Stop the recording. Thank you. Did you close the? You have to close it. Okay, let me go also. Yeah. That's better for me also.
Start?
Yes, I'm just give me a second. I would like to join so I can follow that recording to make sure that everything's correct. Okay. 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 You know what? Just a second. I want to move this away also. Can we move it away because it keeps going in the middle? Come on. It's always in the middle of the slides and it's a bit annoying. Can you put it in the slides? I'll do that. Put the slide. You're gonna have to move the slide. Okay, so continue with the talk editing. Talk about this and talking with this.
Thank you very much. Yes, thank you for the invitation and really to be here in this wonderful place. So in this talk, I'm going to talk a little bit about our report of recent progress on S-Matrix Bootstrap. Of course, S-Matrix Bootstrap has many motivations that's been applied to various different areas. For example, on trying to find integrable S-matrices, to giving various bounds, for example, the A anomaly and so forth. And so, but in this talk, I will mostly focus on its application to understanding constraining quantum gravity. And hopefully, and particularly in the end of the talk, I will address whether or not celestial approach can help us in trying to constrain this space more. So since I'm talking about quantum gravity, so that means that I want to have a handle to constrain what the final theory should be. And but of course we don't know what if we want to be open-minded and we say that we don't know what the final theory should be, then the only thing that we can control is that at least at the low energy it should look like Einstein gravity, which means that there is a parameter regime where at low energy you will have an expansion that with the first term that is Einstein gravity, and then you have a higher dimension operator corrections to the term. And therefore, the most conservative way of approaching, or one of the conservative ways of approaching quantum gravity, is to ask these coefficients to encode the information of the completion, and ask what are the allowed values for these coefficients. Now, of course, already at this stage, you can already make two different kind of assumptions about the completion. One is that you're assuming that gravity is completed while it's still weakly coupled. What that would mean, if that's what you if that's your underlying assumption, then what that means is that when you normalize everything in terms of dimensionless coupling, then you would have an overall n Planck here, representing that you're still at leading order in n Planck, and you have a new scale that is much smaller than n Planck that is coming in that serves as the cutoff for these operators. So this action, the effective action would be what you would assume if you assume that gravity is weakly coupled while it's UV completed. On the other hand, if you assume that gravity is UV completed while it's strongly coupled, then the natural thing that you would put here will be just n Planck itself, because that's the only skill that you're allowed to use. So these are the two distinctions between what you mean by quantum gravity. And of course, as we know, the string theory provides an example of such completion for both cases, because we know that string theory, the scale is set by M string, which is related to n Planck by G string. So when G string is weakly coupled, it provides a solution that takes this form, and when G string is finite coupling, it provides a solution in this form. So of course, then once I frame it in this way, then the natural question is, what is this? Can we actually confine the space of these couplings? And by confining them, of course, we just ask what are the fundamental principles and apply these principles and look at what these space or how the space look like. So how are we going to do this? And so this is where the S-matrix bootstrap come in. Of course, so let me just first start just show you what the distinctions between perturbative completion and non-perturbative completion. Try to estimate what are the problems that you might encounter. So first, let me start with the perturbative completion, which means I just have n plank here, just at tree level, and then all these higher dimension operators are controlled by just a cutoff that is below n plank. Then what this means is that the low energy part, the relevant low energy amplitude that you're supposed to look at, takes this form. So it has, for example, an R-4, which is the Einstein-Hilbert term. It will have potential massless poles coming from the exchange of operators associated, exchange of graviton associated operators of R2 R3, which modifies the three-point coupling. And then you're going to have an infinite number of polynomial terms, which can be linearly matched to these higher dimension couplings. So this is what your IR amplitude, or the IR amplitude that you care about looks like. And because it takes this form, so it's besides from pose, it's basically analytic. So that means that you can just start with assumption of the existence of a UV complete amplitude, and then just pick out these coefficients by doing contour integrals. And the reason is because you know that in the analytic structure of your amplitude is basically going to take, roughly speaking, this form, where you're going to have poles, massive poles and branch cuts coming from the UV completion. And around the origin, which is low energy, it just takes this form, which is just completely regular except for some simple poles here. And therefore, if you want to pick up these coefficients, you just define a contour integral of this function around here and around the origin. And you just, whichever order in S you want, you just take whichever order of the denominator you want, and you can do expansion T, then you can extract your coefficients from your amplitude. Okay, so if you can bootstrap this amplitude, then from this amplitude, you'll gain information about what these coefficients looks like, and therefore you know what these higher dimension operator coefficients should be. So this is for perturbative, everything is straightforward. For non-perturbative completion, which is usually what the problem arises, is because now remember that you might ask at this stage, why am I not considering? Why is the low energy amplitude looking like this and not have any graviton or massless branch cuts? Because that's the usual thing you might worry about. But this is precisely the reason, the manifestation of the fact that I'm assuming perturbative completion, which means that the amplitude is already UV completed even at leading order and incline. So any graviton loops are higher order and incline, so this is relevant to my question. So in this kind of bootstrap, I don't care about graviton loops. So I don't care about any quantum correction, any massless cuts. So this analytic, so the analytic plane looks like a dynamic structure, and the complex S plane takes this form. If you're going to non-perturbative completion, now you don't have that luxury because we cannot assume that graviton loops are suppressed because basically any finite graviton blank, and therefore that means that the relevant IR amplitude will take this form where now you must have terms that are associated with massless cuts. And of course, that leads you immediately to a problem, which is how are you going to capture these coefficients from your amplitude? Because now the analytic structure is that you have a massless branch cut cutting across the entire complex plane. And therefore, it doesn't make any sense to do some contour integral along here because you have a branch cut. So that's not a well-defined analytic operation to do. There's various ways that are now on the market to try to do this, and it matches very well with physics, and that is to, instead of defining coefficients that are associated with around the region, either you can move define new coefficients that are symmetrically moved away from the real axes, it's symmetric so that the coefficient that you get is real, or instead of trying to define things from the origin, you define like what is called low energy arcs. You try to integrate things along amplitude along the arc. And either way, fundamentally what you're doing is you're introducing a scale. If you're moving away from the real axis, or you're introducing an arc, there's a radius for your arc. In both cases, you're introducing a scale. And of course, that's what physics tells you that you should do, because whenever you have loops in your correction, that means all of your coupling constant are running. And therefore, when you talk about the coupling constant, you must precisely tell me what scale you are, and because everything's going to be RG running. And so it makes sense that in order to define your coupling, we should define it in such a way that you scale. Okay. But this is very complicated. Then the thing becomes slightly complicated and trying to do Bootstrap here, because now you need to know what, if you're integrating your IR amplitude around here, so you need to know what is the branch cut structure here, which, of course, if you're just looking at a one loop amplitude, you can compute it, and if you know what the branch cut structure, and then you can plug it in here and see how it affects your coefficient. But if we're doing Bootstrap, you're not supposed to know that. And so then then you need to have a new parameterization of what a well-controlled parameterization of what the branch cut structure can be and how to parameterize it in an independent way. And so this is usually the challenge that you have for an operative completion for Bootstrap for masses particles, masses interaction. So the way that I'm discussing it here, you'll see, you probably will expect that I'm not going to talk too much about but I will present some results which tell you why they can evade this kind of problem. Now, so let me continue. So good. So now we're going to do Bootstrap, and what Bootstrap means is that I'm going to constrain that amplitude just using fundamental principles. So what are the principles that we have? So I'm listed here. First is basically unitarity, which tells you that the S matrix square must be smaller than 1, and therefore when you expand it from 1, by the way, this is just then you can just take a 4S matrix. I have a J here which represents the spin, so I'm really expanding it on some orthogonal basis, or these are just partial waves. And of course, you have the identity part plus the imaginary part, and this imaginary part is basically just take your amplitude and then you expand it on some suitable orthogonal polynomial. So the reason I just write orthogonal polynomial here is because the corresponding orthogonal polynomial will depend on the space-time dimension. It will depend on what kind of things you're scattering. You're scattering scalars, and this is a well-known Eigenvalue polynomial that you should put there. But if you're actually scattering spinning states like gravitons, photons, things that carry velocity states in 4 dimensions, that these polynomials are something else. These are, for those who know, these should be the usual Wigner D matrices, which has a velocity dependence. But anyway, these are just orthogonal polynomials that they expand on. And then solving this equation will give you basically just the absolute value square of the individual expansion parameters should be bounded by the imaginary part of it, weighted by some numerical factor which depends on the dimension. So this one we call nonlinear unitarity because it's nonlinear in terms of these partial wave functions. You can simplify this to linear unitarity, which would be a weaker constraint from the nonlinear version, which just tells you that the imaginary part must be bounded and bounded above. And finally, which is actually most of the activity that has been going on in the S matrix, is that the most weakest constraint is just that this thing has to be positive. And that's actually where most of the activity has been done so far. Although people have already started to come into here and proposing more and more constraints. And this is actually usually comes with also is related to as the optimal thing. So this is unitarity. Assume that amplitude is unitarity. The second is causality, and this can be more. And causality becomes more manifest in the near 4 limit. So this is basically the statement that a near 4 limit 2 by 2, the 2 to 2 scattering amplitude, you can prove that it must be bounded by S squared. So there's many of you probably heard of Rosal bound, which also has which gives you a bound on the amplitude, but of course, if you know the Rosal bound, you also know that it doesn't apply to masses to a system which has a gap. There's various ways of seeing it. That's related to the fact that if you don't have a gap, then your amplitude essentially will have what we call a p-pole, and therefore, in this proof, this will destabilize the proof. Of course, now since we're interested in gravity, so there's various people who looked into this, and now there's various arguments which you can establish rigorously about this S squared. And one of the nicest way that so one of the nicest. So one of the nice ways to understand this is to understand this from ADS CFT, where instead of a class-based amplitude, we would talk about scattering amplitude in ADS space, and we take the class-based limit. Since the scattering amplitude in ADS space corresponds to CFT correlation functions on the boundary, now you can go to the higher to the regional limit of the correlation function and extract the analytic behavior. You take the class-based limit, barring issues about whether or not these two operations actually commute with each other, you can argue that the amplitude is a or even in the gravitational case. So this would be an example. And finally, analyticity, which is basically just a statement that of the previous graph here, that away from the real axis, when t is small, there's no singularity on the complex plane. The only singularity are associated with threshold singularity for particle. Okay, so this is the ingredient, and then we can start to do the cooking. These are the constraints. So how exactly do we do the cooking? Well, as I mentioned before, so let's work with the perturbative completion. So these coefficients, as I mentioned before, are related by a complex, by a contour integral of, let's say, assumed UV completion and the derivative expansion t. So we're defining these coefficients by using a contour integral here. But now I can, because most of this is analytic, so I can deform the contour into here. And the difference will just be picking up the poles, the residues of the poles and the discontinuities across the branch path. So this immediately tells you, so the GKQ, which are the polynomial coefficients, which are linearly related to your higher dimension operator, can be written in a very simple form, which is related to the infinite. So you can write it as an infinite sum over contributions from the poles and contribution from the discontinuity. And of course, importantly, because we know that that these things are supposed to be expanded orthogonal polynomials, so you can rewrite this in terms of expansion on the orthogonal polynomials. And identifying the expansion coefficients as precisely the imaginary part of your partial wave expansion, you immediately see that these things must be positive. And the whole Bootstrap program basically starts by trying to bootstrap the constraint on your coupling on these higher dimension operators, enforcing that these has a positive expansion. So there's many methods on the market to explore this constraint. You can either explore it numerically using linear programming or semi-definite programming, or there's also analytic understanding, which I will mention briefly about it. But so let me just show you an example of the results. So previously here, this formula was just for scalar interaction. So let's go to the real thing. Let's talk about graviton interaction. So graviton, when you have graviton, you have various different helicity states. So that means you're bootstrapping multiple different sectors of amplitude. And so the dispersion relation is basically a statement of this equality, where this equality is understood in terms of a polynomial matching of both sides. So here on the left-hand side are the amplitudes of the polynomial expansion. It goes the coefficient of the higher dimension operator. The polynomial expansion in S and T on the right-hand side corresponds to what you would get from the imaginary part of this continuity of your amplitude expanded on the partial waves. So here you see that partial waves are actually Wigner D matrices, which actually depends on spin. So you can, as I mentioned, there's various different things that you can get on your.
So I have like a really dumb question for you. Just looking at these, I see that in pure Einstein gravity, outline.
No. So this will be something that you can impose. I mean, yeah, certainly, because by the way, in stating all this, what you should know is that, for example, in all string theory solution obviously will satisfy this, and so any amount of supersymmetry breaking will always satisfy this, and of course, then that means that all plus will be there when supersymmetry is completely broken, which will still have this expansion, so this cannot show that all plus is. So okay, so this is one of the state-of-the-art boundaries that you can carve out currently. So this, well, first of all, it's already very non-trivial that we actually see from these various principles. You can see that the space is actually constrained to a finite region. So this is associated with B8R to the 4. I'm picking this operator out of B8R to the 4. And so the 8R to the 4 operator, of course, has various different tensor contractions, which means that it's actually various different independent components. So I'm just picking 2 of these components and taking the ratio. And so these are just comparing with previous literature plots, and now the best boundary is here, which we believe is stabilized, irrespective of how many derivative orders it pushes essentially stabilized here. And so you see these, so it's nice that we have a boundary region, but you already see that, but you can see that this is far from ideal, because we can plot various 3D completions by 2D heraldic string. You can also generate these operators just simply integrating out massive spinning states. And they all lie here, so they're inside, so that means that we're doing something correct. But they're really isolated in a very tiny corner inside this allowed region. And I'll talk more about that in 2 slides. But you can also, I'm just showing you that you can do this with various different operators. And in generic cases, the theories, so in here, I'm comparing the ratio between D4, R4 with respect to R4. Now there's more, so even though they're all inside, you can start to see there's some distinction between strings. And so here, when you're really just looking at the same coupling, meaning the same derivative order, you don't see that much difference between equal field conditions. But one, yes? You mean, do I know what are the theories on the boundary? So of course numerically, then you don't run into the program. But of course, then you would like to understand analytically, which we do have a particular understanding. So let me just already mention here. So usually, what actually sits on the boundaries are actually, if you actually are able to look at the solution, the spectrum solution, are actually solutions that only have finite states, finite number of states in the spectrum. So, on the one hand, you know that any physical theory doesn't have that, because we already know that there's should be infinite number of states in the spectrum. And so, and of course, the reason that you have these kind of finite spectrum solutions on your boundary is really more a reflection of the fact that you're always truncating a particular derivative. So you can satisfy all the conditions using the finite spectrum at this particular derivative order, but you know that starting from the next derivative order, you have to redo the thing. Yeah, so this is also one of the things that is so far the challenge in S-matrix compared to CFT Bootstrap, is that so far we haven't been able to corner anything like that. And so this is something that we would like to achieve, to do in the future.
Sorry.
Yes?
You're talking about this perturbative.
The perturbative completion, yeah.
In the non-perturbative, it was, I mean, people did find.
Yeah, I'll mention about the non-perturbative. Sorry, yes. I mean, it's not exactly on the boundary either. I mean, it's the numerical. You're talking about the Pedro-Vieira, the bonus, and
Yeah.
where's string theory.
I mean, okay, that's one example, but if you do the 2D cases, then you have all the
Oh,
integral.
yeah, sorry. So I'm talking about gravity here. Sorry.
Okay.
Talking about, But yes, indeed, as I mentioned, the S-matrix Bootstrap has been applied to various different problems, and one of the problems is to find integrable systems, and that will be that you want to do Bootstrap in 2D, the 2D S-matrix. And there, in some sense, you see that the integral systems do lie in the boundary. Right. In some sense, I would say that the reason, I mean, whenever, sorry, so this is my private feeling. So whenever you want to find a theory on the boundary, that will mean that the theory is not really different. It's not easily deformable. So if you, for example, an integrable system, you would have only like some marginal parameters that you can actually deform, and you would expect that these can start to appear at the boundary. But if you think that most of the theories that we have that we know about in gravity, string theory, there's tons of deformation things you can do to it. So in some sense, it's not so surprising that string theory is lying very inside of the parting not so far. Okay, so was there any? No, it's. So okay, let me just jump a little bit. So I mean, just various different plots, and the purpose of these plots is really just to show you that string theory completion are still deep inside what it's been able to, what people have been able to do so far. By the way, so this is the all plus amplitude, so you can see that the all plus amplitude region, first of all, it's not zero. And of course, many of the completions are actually supersymmetric, so they actually lie in a place where one of these one of the axes would be zero. But in principle, from the Bootstrap point of view, the all plus amplitude does not have to. Okay, So what can we do better? So here, this is some indication of what's missing. So again, let me just look at this plot. So this is the allow region. So this contour plot, what this is doing is this is actually holding some of the coefficient fixed. So what this plot is doing is holding B40. So this will be the AR4 with respect to R4, holding them fixed. And these are the different fixed contours. So you'll notice that here, this contour is actually corresponds to the value being that ratio being extremely small. This is slightly bigger, this is bigger, and this is bigger, and this is bigger. Okay, so what that means is if you look at this in a 3D space, it's essentially very flat. And all of the known theories are sitting in this tiny slot here, which, because this is holding one of the couplings to be fixed, so this appears to be telling us that there should be lower bounds for the known theory. Because these are where the ratio is going smaller and smaller and smaller. So the fact that everybody lives here means that the known theories cannot go outside. So if we want to, so one of the hints that what is missing is probably is that when if we can find new principles that actually will show us that that these couplings should have a non-trivial lower bound. Yes, actually, this, strictly speaking, this is a line, but the string theory completion doesn't lie on the line. Yeah. The reason that you can understand that why these are lines, these are field theory completions, and the only difference from them are just the different spins of the massive thing that they're bringing out. But it's essentially just a one loop thing, and so the spin effects don't affect particularly this kind of operator. And so this is the field theory part lies on the line, but the string theory part is off that line. Okay, so so another thing that one can do is, as you see here, I'm really probing higher derivative couplings. So these are 8 derivatives. Right? So you want to go lower derivative because these are really the lower the derivatives are more accessible to experiments, and these are leading corrections. And of course, if you want to go to lower derivative ones, then what happens is that you encounter the so-called graviton problem, which is the statement that because you have a graviton, that means that anything you're scattering has a graviton exchange, which means that your amplitude will have at least an S squared over T. And so if you're trying to do any forward limit dispersion relation, that T equals 0 singularity is telling you that the dispersion relation is not converging at the forward limit, because it has to reproduce this T-pole. So that means that this infinite sum that you're working with is not a convergent. So that's the usual the T-pole, and that only affects operators essentially with 4 derivatives. And the higher derivatives that you consider, you're not affected by this non-convergence, which is why I was looking at higher derivatives before. Of course, you will immediately see, but then this is not quantum gravity. The whole point of gravity is this T-pole, that it has a long-range force. So really try to do. And indeed, Simone Kermoid and collaborators have developed a way to address this problem, and which is to try to, instead of working in momentum space, they do a Fourier transform to impact parameter space and try to do this kind of bootstrap and impact parameter space. So therefore, I mean, in a nutshell, what they do is, so this is using very parameterized higher dimension coupling, and you see that they have T-pole here, and your dispersion relation. So instead of just working with this dispersion relation, you try to integrate these things over some functions, and try to find certain functions that are definite positive to the bootstrap, and they can find such functions, and then you can do the bootstrap there. So this will be like integrating across P, which is just essentially for your transform. The price you pay for the T-pole is that the plots you get are something like this. So this is the R4 operator, this is the R cube operator. You'll notice it's normalized with respect to the infrared column. So that's the normalization of the T-pole. You get bounds on these things, but the bounds are always normalized with the log function, the cutoff. Of course, the natural thing that you would put in the cutoff would be, for example, the Hubble scale, and then you can play around and go back and relate to minority, extract non-trivial constraints. sorry. You mean instead of bootstrapping asymptotic states that are single particles with an address state? Yeah, actually, this is what I will talk about. I mean, so this is what I want to say to talk about a little bit about how my services here. But so far, there's nobody that one that I know. Okay. So all of that discussion was only about perturbative amplitudes. Perturbative PUD completions. You can talk about non-perturbative, and I think, as I told you already, that the non-perturbative, if you try to do things non-perturbative, the problem is that you have this massive branch cut, and this massive branch cut causes you to lose control of how you parameterize things in the infrared. However, in certain cases, which was utilized in this very nice paper, which tried to bootstrap this problem non-perturbatively. And here they're considering the theory in 10 dimensions, and they're considering the R4 operator. So this is the way that you parameterize it. This is the Einstein-Hilbert term. This is the R4 term. Now, because we're in 10 dimensions, so the infrared divergence, the masses cut coming in, actually starts at higher derivative than R4. So if you're looking at just the pure R4 coefficients, it's actually not, it does not suffer from this masses loop issue that cuts through. So you can define, so here, because this is R4 and not corrected at one loop or any loop, therefore you can define unambiguously this coefficient from the amplitude without worrying about the masses branch cut. That's what they do. And since they can do that, and so what instead of trying to do a near forward limit dispersion relation bootstrap, what they do is they just write down an ansatz coordinate. This ansatz, of course, is very, very well motivated in terms of giving you something that is analytic and complex claim is set on real axes. Of course, this ansatz is in principle infinite because these polynomials can go to infinite order n. So basically, what they do is they build this ansatz to particular order n. They imply just throw in the whole kitchen sink on this amplitude required to satisfy this everything you can think about if you try to impose it on it, and see the minimum value you get for this coefficient alpha. And then you move to the next order. You increase n to n plus 1, and you do the whole thing again, n plus 1, and you order and see when this converges. And so this is so that's why you see this. So this is, of course, there's actually two truncations. One is truncating your ansatz, and the other is truncating of your spin, because they're doing unitarity bounds on your partial waves. So you're always doing particular spin order. And so you want things to converge both in the spin limit and in the ansatz limit. And so this is, so you see that it's converging here, and also it's always converging to a flat loop here. And at least the current numerical bound that they get a lower bound here, and the lower bound is 0.13, and here are basically the string theory values. Of course, the string theory value, the most interesting is the 2p value, because it has a parameter how far we can tune various places in your strong coupling. And you see that in some sense, string theory is actually saturating. It's very close to this bound, and it's basically covering the whole space that are allowed by this bootstrap method. So at least in this very tiny constrained problem of asking, does string theory cover all the possible value of the 10-dimensional maximal supersymmetric completion of gravity? At least in that, with respect to this coefficient, it does appear to be things that string theory is covering all possible values that are allowed from the bootstrap program. Now, so notice that I'm saying that here there is a lower bound, and so this is a non-perturbative completion. And, sorry, actually, how much time do I have?
5 minutes.
Right, okay. So and yes, and as I mentioned, that when you're looking at this graph, it looks like what you need is you want to introduce some lower bound. And therefore, you might ask the question that, hey, in their non-perturbative completion, they actually get a lower bound. So maybe that's the point, that you should impose some more non-perturbative information. Of course, we already started out saying that we're trying to do perturbative, whereas the previous bound were for perturbative completion. What do I mean by non-perturbative? but still there might be some UV coupling that can still be non-perturbed. So I should probe the possibility of doing a bootstrap where I'm still perturbed at end point, but I'm not assuming I'm perturbed and the remaining coupling. So any other coupling other than end point is going to be can be non-perturbed, and maybe we can try to do something like that. So this is indeed what's been done. So at least what's been done so far now is to try to do the upper bound of your now import instead of the partial wave being positive. Now I'm introducing upper bound here. So to do this, in numerical, you have to do linear programming. You can try to do that, but let me just skip the details. You can do it. There's actually a very nice picture behind the numerics, which basically tells you what exactly is the space, and this, and which has a very precise statement in terms of mathematical geometry, which is essentially these are all related to what is known as the convex Hall of moment curves. So you just consider a moment curve and consider all the points in a moment curve and consider the convex Hall of it. That actually gives you the space. And to map from the dispersion relation to this geometry, it's just some very simple GL transformation. But anyway, it's not so important, so I'll just, if you just care about the final answer, so let me just, I think it's too much. So let me just skip to the final answer. So if you know that geometry, then all you need to do is that in that geometry, instead of just the convex Hall, where you're summing all the possible points with positive value, now you're summing all the possible points with the upper bound of your positive value. That translates to a mathematician called the L moment problem. And we can import some knowledge of that and derive analytic bound. So this is the analytic bound that we get. Or now you see that the couplings are no longer ratios. The reason it's not ratios, precisely we have this upper bound. So these are no longer projected. So this was early this year, and in July, 2 months ago, numerical methods have developed the area of the computing. So you can see these are exactly the same graph. So in some sense, we have an analytic understanding of what is the space. But again, we were only looking at things that we are interested in, which means that we were asking if imposing this upper bound of your partial wave does improve your graph. So previously, okay. So if you, I'm just enlarging this. So remember the previous graph where I showed that triangle and all the theories are lying in the middle. That is actually a projected graph, which means that you're talking about ratios of your coupling. So if you're talking about ratios of your coupling here, then you're really talking about the range of the slope. You'll notice that this slope, even though the upper bound you impose carves out a smaller region, but the slope is still saturated by the known bounds. Sorry, so it's still saturated the previous bound. So it doesn't alter the slope at all. And actually, this is a further result which was coming from the numerics, which actually imposed a full knock of the full unitarity. And you see that the slope is still unchanged. So even though the region is changed, but in terms of the ratio is still the same as before. So in other words, it looks like asking if things being perturbed and not perturbed unitary. This constraint doesn't actually improve the space. It's still the same space that you look for. So this is not what we're missing. So what are we missing? Why is there still so much space out there? So actually, so I'm going to present two possibilities. So first of all, this should not be surprising because in history, it has been littered with 4-point amplitudes that satisfy all the fundamental principles. But you didn't hear about them because they're not a theory. And the reason that they're not a theory, at least, for example, the famous, Kuhn's amplitude, or for example, Lovelace-Shapiro amplitude, which actually has being unitary, a string theory-like amplitude that is unitary in 4 dimensions. The reason is people didn't find the higher end analog. In other words, people just had this nice 4-point amplitude which satisfied all the properties, but the endpoint generalizations such as the Venezano amplitude was never found. And in fact, even more modernly, we already know how to deform the type 2 string amplitude in a control way. So all you need to do is just take your favorite type 2 string amplitude, just deform by this deformation parameter, multiply by this term, again multiply by R4. And you can show that this amplitude is unitary in any partial wave expansion as long as epsilon is between 0 and 1. Okay, so there's various different deformations which can deform known theories at 4-point level, which satisfies all the criteria. So maybe it's not so surprising that you find that you cannot bound anything, or you cannot, or so far we haven't been able to really corner single in any sense. And of course, there's even more dramatic UV completions which actually have accumulation. So what might do? So we can think about what actually finding a higher point amplitude actually means. So when you're looking at higher point amplitude, in some way, what you're really saying. So let's talk about things in cubic interaction. So for masses, 4-point amplitude, you're really talking about consistency condition between the 3 massless and 2 massless, 1 massless interaction. So you're talking about these 2 kinds of consistency of these 2 kinds of interaction. If you go to 5-point, if you have a consistent 5-point amplitude, then now a new vertex comes into play, which is actually the 2 massive, 1 massive. So you see that as you go to higher and higher point, if you have a consistent amplitude, one way to say that the new constraint you're imposing is that you're imposing that all of these different degrees of freedom are all consistently interacting. So that's what you can view it from this point of view. And therefore, with the same consistent condition, you can also implement it by actually requiring that you only sit at 4 points. But now we try to ask that these internal states become consistent, also they become external states. So this will be a mixed bootstrap problem, where now it's not just the same set of sectors, we're actually doing bootstrap across all the different sectors within your system. And so this is one of the things that one can try to do, and indeed people are trying to do. So this is another nice paper in April, which is actually answering another question, not in terms of gravity, but trying to talk about dilaton interactions and the A theory. And there they already start to develop the machinery to do this kind of bootstrap. Of course, to change it to spinning states and with graviton flow, that requires 2 more numbers. But this is one criteria. Yes? Yes. So in this paper, they don't have the massless flow. Right. So that's still not kind of complete. But what we're trying to propose is to try to do this kind of mix when the system actually has a massless flow. Oh, you mean that? So your question is all of the exchange guys in the outside?
Yeah.
Yeah. So in this paper, no, they're actually not there. They're only just picking one. Yeah. So of course, then you want to do is to consistently put down one. Yeah. So there's 2 things that you need to do is put all these waves systematically on the outside and put things and along with the graviton. So this is one direction that we will try to do. And another direction is to try to think about this in a celestial context. So, of course, a very nice paper with Huang, Ricardo, and of course Andy here, and where they discuss how if you view the amplitude, if you view the celestial sphere amplitude, but instead of usually talking about the analytic behavior in C, you talk about analytic behavior beta, which is the conformal dimension. Then you can also see when you have EFT amplitude, EFT coefficient, you can extract the EFT coefficients at beta equals -2 here. And then you'll see a bunch of poles because if you know that low energy in terms of omega, it's going to be polynomials. So that means that this integral is going to pick up poles at negative values. But now you can make a distinction between field theory and quantum gravity completion, because on the positive real, so this is a negative real line with a pole. But on the positive real line, because field theory is power law bounded, which means it has a big expansion and omega going to infinity as a 1/omega expansion. So that means that you're going to have non-trivial poles for any power law completion, you're going to have non-trivial poles on the real axis. For quantum gravity, because of the black hole microstates, you know that in principle that the high energy behavior should has an exponential omega square suppression. So this will be on my last slide. And therefore, tells you is that there's going to be no pole on the real view. So the question is, can we actually start to do Bootstrap on the celestial sphere view, since it actually has information both in terms of the IR couplings, and we can start to impose, because actually, so previously in all the Bootstrap, all one is imposing is that the real core limit is bounded by S squared. So you would like to know that the amplitude has actually had this, so to have this behavior for gravity. So that's what we like to do. This is a possibility. And I think the tool is available. So the only, so this is part one. So the only thing that is problematic in trying to do Bootstrap on a celestial sphere in terms of amplitude point of view is that in principle, as we know, that the 4-point amplitude lies on the equator, and it splits into 3 different regions, and 3 different regions are in principle different functions. It corresponds to whether or not 1, 2 is the incoming, or 1, 3 is the incoming, or the STU. It appears as different. The physical region of S channel, T channel, U channel are actually 3 different functions. And so then you have to talk about how to analytic continue from one direction to the other to impose crossing, and that becomes a problem. Yeah, there's a lot, and you can do that in principle, but yeah, it's not so simple. So on the other hand, what you can try to do is to actually start with this representation of the amplitude that is already crossing symmetric and project it onto the celestial sphere. So I imposed crossing already at the amplitude level, and so this was done very nicely by Singha and his students, where they use this crossing symmetric dispersion relation that represents their amplitude. So their amplitude, even though it's a function of ST, the representation is completely crossing STU symmetric. It's defined in terms of STU symmetric variables. And then you take this, and then you can just directly project this onto the celestial sphere. So this will be the dispersion, what the dispersion relation will look like on the celestial sphere. And what one can do is to start with this equation and try to look at the poles at beta equals minus integer, which gives you the different derivative order, under the constraint that on beta equals a positive integer is 0. So this will be imposing the fact that exponential has an exponential minus omega squared suppression. And indeed, you see that in principle, in terms of this dispersion relation, there is non-trivial poles at the positive as a must. And therefore, a potential new way. So let me just, one last bit, one comment is that just by using this dispersion relation to bound the Wilson coefficients without imposing positive beta is equal to 0, it's already been done actually in this paper, and you can get similar result that we've done before. So this is the next frontier, which is now can we actually controllably impose a constraint that actually on positive beta is 0. So that would be telling you that your theory actually has a black hole, and that's the next thing that hopefully we can do and see how much more the space changes. Okay, so thank you very much.
I think we're going to take questions later because we're a bit planning.
Okay, sorry.
During the discussion for sure. Oh, Andy comes. Okay, okay, let's go on. Sorry. Go on.
But now, recently, so the problems that you have in the different regions but in the last few months, some people have very different methods for teaching or background. I wonder if by combining you might get more practical.
Yeah, so the challenge, well, not the challenge. Well, the challenge there will be to impose in those background. What do you mean by material? So the whole bootstrap principle we were implying is that we have a well-defined notion of utility, and we define it on our S matrix, and then use this constraint, and actually, yeah, and so of course we can consider different observables with different backgrounds. Then I need to reformulate what actually do I mean by unitarity there, and then I will import that information.
It's just the assumption that you don't have branch. That's
Yeah. Well, and that depends on, yeah, well,
Unless you make some very special choices.
but I will say that yeah, there's various way of getting away from of overcoming crossing signals. And already here, this is already a way to get across it. So you just see how the constraint of theta equals positive integer is 0. At 0 poles, how this looks out in terms of constraints. But yeah.
Yeah.
Yes. So just to comment on the exponential progression. So it's true that, I mean, there is an angular dependence that business is not just an energy thing. And it's true that for large angle, this is a signal black hole, but at small angle, this is just the emission of radiation.
Yeah, but you needed to because of the fact that you're doing the whole quasi symmetric dispersion, so it's not a fixed angle dispersion, so it has to be, in order to implement this, there has to always be a generic angle. Yeah, I agree.
Right, no, yeah, sure. But then you think there's not much control of that angular dependence for radiation and the black hole. Is this crucial or
You mean whether or not this exponential minus omega squared is always minus omega? I mean,
like the angle dependence?
oh, the angle dependence